I see. Please.
Okay, sure.
Okay, so hello everyone. Welcome to today's quick special seminar. It's very happy today that we can invite Carleton Coffrin from Los Alamos National Lab. He's a staff scientist at the Los Alamos National Lab, and also he's leading the Advanced Network Science Initiative. His research interests focus on how optimization algorithms can be applied to applications on infrastructure networks. And his background spans many forms of optimization, including mathematical programming, constraint programming, and local search. Recently, Carleton has been exploring online learning via open online courses and also YouTube videos, as well as mobile computing architectures. So today, he's going to give us a talk on some applications, unexpected applications for analog quantum computers. Let's welcome Carleton.
Thank you very much for the introduction, and thank you to Shadi Wu, who's online, who kindly hosted me on this kind of odd day. I happen to be passing in the area, and I had never been to Quicks before, so it's a pleasure and an honor to be here and see the place I've heard so much about. I'm going to talk about a lot of quantum simulation and applications of quantum simulation in this talk, but first, let me begin by trying to understand who you are a little bit. So I am a computer scientist by training. This seems like a very great place for that. I do optimization, designing NP-hard algorithms, but lately I've gotten a lot into quantum information and how we might use quantum computers at a big national laboratory like Los Alamos. So begin by just showing me, raise your hand if you would self-identify as a computer scientist. Couple people. How about a physicist? Okay, good. I'm very glad to see that because this is going to be mostly a physics talk. And please cut me some slack because I'm a computer scientist by training, but I think this is a great example of where these fields can come together and do something really impactful in the future. So let's just dive right into it. So I think we all know in this audience that, according to Google, at least, we have quantum supremacy. So, and this happened a long time ago. This was pre-pandemic paper, right? So I guess the natural question I would say is, like, given we had a really big deal about this back in 2019, where's the impact? Why, like, are we totally changing the world right now with quantum computers? Or, why isn't every big company running out to buy one and install it on their facility? And I think there's a good, reason for that. The current new frontier is to show a practical quantum advantage. So this type of a paper, I think, did a pretty good job showing that there is some contrived computational task that can be done, which on that type of a NIST device that just cannot be easily simulated even with a huge supercomputer. But you might have hoped that after that was demonstrated, they'd like open the floodgates of cool applications. It does not look like that has happened. So now we're on the practical quantum advantage. Like, when are we going to start impacting real things? And, my assessment of the vibes out in the community is that this is pretty far off. Maybe it'll happen in 5 or 10 years. Maybe it will take longer than that. We're not really quite sure about when that's going to come. Now, here's the crazy thing. Throughout this talk, I will try to convince you that practical quantum advantage is already here, and nobody realizes it. So that's, I think, a pretty big and crazy thing, but let's see if we can convince you. And if you want to talk more about it, I'm here for the rest of the day. I would love to, pick your brain about these things. So the first thing to understand how this could be possible is to recognize what I see as the quantum information science and engineering blind spot, and that is these analog quantum computers. So the way that the impression I get from the broader community goes something like this. Preskel wrote this really influential paper that defined the term NIST, which we all use. It's basically a widely used noun these days. And this is a really cool paper. It's very long. Do me a favor, raise your hand if you've heard of this paper. Okay, so it's almost everybody. Keep your hand up if you've read this paper. I have not read this paper, okay? It's a long paper and there's a lot of good stuff in there. Fortunately for me, I have good collaborators who do read a lot, and so they've read the whole thing. But if you dig into this paper, around section 6, subsection 10, there's this discussion of digital versus analog quantum simulation. And it says, I'm just reading verbatim here, we can anticipate that analog quantum simulators will eventually become obsolete. And that's because they're hard to control and they will someday be surpassed by digital quantum simulators, which you can get total control over. Now, I think this type of opinion is shared by a large part of the community, and it leads to the following logic. It's like, okay, well, analog quantum computing might be useful now-ish, but it'll be dead in the long run. So, corollary, people who work on analog quantum computing are just, that's a dead-end research area. Don't waste your time on it. But let's pull the thread on this thought a little bit. The core claim here is that one day analog quantum simulators will become obsolete. So let's just imagine we're in a far off future where we have fault-tolerant quantum computers that have, no errors at all, and we're just going to do quantum simulation on them. It's going to be perfect. And at what point or what properties would that quantum computer need to be better than the analog quantum computer? Now, I'm going to use as a reference point an analog quantum computer that we have today. So I would say the most widely known one is D-Wave's quantum annealing platform. This isn't the analog quantum computer I would dream of having. I would love to have one where you have like much more control than this. But this quantum computer implements one analog algorithm, which is called quantum annealing, and it has a bunch of restrictions, but it's a really, really big computer. I'm picking this example because a lot of people think this hardware platform is like not interesting or not computing something really impressive. I'll try to convince you otherwise on this slide. So on the right is a paper that was recently came out in the last year by D-Wave in Science or Nature, where they did a out of equilibrium Ising dynamics experiment. It's very similar actually in flavor to the kicked Ising experiment that IBM did last summer. So if you're familiar with that paper. But here's the basic properties of the system. We're going to do unitary evolution of the transverse field of the Ising model in a system with 5,400 sites, so they're qubits. and a sparse 3D lattice structure, which ends up having 13,000 2-qubit interactions. So it's a 3D-ish structure. We're going to evolve this system for 30 nanoseconds at an energy scale of 1 to 5 gigahertz. In practice, the total annealing time is like on the order of 30 nanoseconds. However, you have tons of overheads to program the machine, to read data out of the machine, stuff like that. So in general, we can think like this whole quantum simulation on real hardware takes 1 second. So we're just going to say, to do that whole experiment that's in this paper, takes 1 second. Now, what type of fault-tolerant quantum computer would you need to replicate this particular experiment? I'm going to assume that you have an ideal fault-tolerant quantum computer. It's going to have gates in the Clifford plus T gate set. Maybe that could be better in the future, but it's a reasonable assumption for now because that's what the surface code implements. And then I'm just going to assume every gate operation is 25 nanoseconds. So I think that's pretty optimistic based on current hardware. Basically, we're saying like for 25 nanoseconds, you're going to apply a Clifford plus T gate at perfect precision. There is 0 quantum error. And then let's just look at how long it would take to simulate this type of thing. We're going to, we have to pick how we implement it. We're going to do second order Trotter-Suzuki for discretizing the time evolution. We're going to request that accuracy of the energy that we get at the end of the simulation is on the order of 2 digits. Maybe that's too low. But ultimately, this results in, we need a gate depth for a single Trotter iteration of 4,000. And we need, 9 million steps of this Trotter step to do the continuous time evolution, because this is time varying Hamiltonian. That number is probably too high. We could use more clever algorithms, but I think this is a good, first approach at how you'd simulate this thing. So you multiply all those numbers together and then times 25 nanoseconds. Let's put it back into seconds. That's the divisor of 1e9. Now you're at 1,100 seconds with no overheads. This is just to execute the gates under this like super kind of optimistic setting. So my claim would be that, if you can tolerate the noise which occurs in this analog quantum computer, it's always going to be dramatically faster than a fault-tolerant gate-based quantum computer. So in this particular scenario I outlined for you, it should be the analog quantum computer you have today should be like 1,000 times faster. Now, that's not like a number where we can instantly say, oh yeah, that's obsolete. That's a number where we have to think, well, is 1,000x faster really useful for me relative to the noise I'm gonna have to pay to that occurs in this device? I should note that this paper by D-Wave is a follow-up to an earlier paper they wrote called Coherent Quantum Annealing, where they made the case that in this range of like 30 nanoseconds, their machine essentially experiences no noise. So the results seem actually quite accurate, but it's really hard to verify because we're in a regime that's not simulatable by classical computers. So I hope I've convinced you at this point that analog quantum computers are not obsolete today, and they're not going to be in the foreseeable future. They do something very unique and different. And we can use them today. So let's use them. So this is the good news. It looks, to me at least, very controversial opinion that analog quantum computers are useful today and in the long run. But that begs the same question of the practical quantum advantage. So what are we going to use them for? So let's just assume they're useful. They're doing something we can't easily simulate, but then what would we really use them for? And that actually is a much deeper question than I ever imagined. And I think you can broaden it not just to what will we use an analog quantum computer for, a specific one, but what will we use any quantum computer for? A good thought experiment is imagine all the quantum advantage demos have been done, right? Everyone is convinced. Then what? What are we going to do? And there's actually this fantastic program from DARPA. I recommend reading up on it. The results from it are coming out like in the next year or so, called quantum benchmarking. And this particular program is trying to answer this question. It's so difficult to answer it that DARPA thought they had to write a whole program on like, what would we really use a quantum computer for? You know, if we further say, we're going to specialize the potential applications to an analog quantum computer or quantum annealing, it just even becomes harder to find a real application of a quantum computer. So it's like, this is hard on squared, you know, to do it with an analog quantum computer. And just to give you a feeling for that, you know, about 6 years ago, Lanel had purchased a D-Wave quantum computer, and all the scientists at Lanel were like, well, what can we really use this thing for? And I think we have now a good application. That's the subject of this talk, but it took us like 5 years to find one. So one really good application of a quantum simulator that, you know, D-Wave can do. So this is a tough problem. I wouldn't brush it aside. So let's talk a little bit about unexpected applications of quantum annealing. I'm going to give you the basic introduction to the computing model. I hope that will be a review for most of you. And then talk about some surprising types of computations you can do with it. There's some obvious ones and then some more surprising ones. And then I'll go into a very specific application we think is useful. First, I should mention, you know, I'm got lots of great collaborators, both at D-Wave and at Los Alamos. Some of you might know John Nelson. He was a postbac working with me some years ago, but now he's a PhD student here. But all great people have helped me do this. Let's talk a bit about analog quantum computing platforms. I mentioned D-Wave quite a bit, but it's not the only one. So you've got QEra, which gives you a different type of analog quantum computing model, but with like different constraints. You've got Pascal, which is in Europe, startup building also an atomic-based analog quantum computer. These, you know, computers range from, let's say, 100 to 5,000 qubits. They have coherence times, and if you do normalized time units like 1/j, you know, they're on the order of 4 to 30. And currently, all of these models only let you do a transverse Ising Hamiltonian, which is really the most basic or most restrictive Hamiltonian. That makes your job difficult in finding realistic applications. So I'm going to focus on quantum annealing, but I would say that like there are many very interesting analog protocols out there. This is just the one we understand the most. Cool. So what is quantum annealing? We'll start with just the classical Ising model. So we're going to have a lattice of sites, which take the values -1 or 1. So that can be interpreted as an up or down spin. We'll have a local field H that can influence them, and then J will be mediating the coupling strength. So on the right-hand side, you have the classical Hamiltonian for an Ising model with the 2-body terms and the single-body term. In the realm of classical computation, there's kind of 2 core things folks like to do with this model. The first one is you might want to look for, say, low temperature spin configurations. So sampling at some effective temperature beta from this Hamiltonian. The other thing people often ask is, what are the ground states? What are the lowest energy configurations? That's more like an optimization task, where you're just looking for a spin vector that minimizes the energy. So, you know, what can you do with a quantum annealing computer? If it's a quantum annealer, it's solving this adiabatic quantum algorithm where you're trying to use the Schrodinger equation and continuous time dynamics to solve, right, this Schrodinger equation and minimize a classical Ising model. The approach that's taken by D-Wave is the following. So they have, on the bottom, you can see the Hamiltonian it implements. So it's a time-varying Hamiltonian. On the right-hand side, you see the classical Ising Hamiltonian's been encoded on the Z basis. You also have the transverse field X Hamiltonian, and that's controlled. These are interpolated over time between like a purely X Hamiltonian into a purely Z Hamiltonian. The blue and green lines here are showing you how you start with a dominated X Hamiltonian, and then you ramp that down while you're ramping up the Z Hamiltonian, which is the green line. And if you do this, I mean, the adiabatic theorem says if you do this slowly enough, you'll arrive at the ground state of the classical Hamiltonian, which may be interesting in its own right. But we're going to focus on a case where actually the full quantum Hamiltonian is interesting and useful. So what are some expected uses of a computer like this? So the first one is you can simulate quantum dynamics. So if it's a fully closed system and it computes perfectly, you can do things like reproduce the Kibble-Zurich mechanism scaling that occurs in closed system quantum dynamics. So, and I mentioned quite a bit in the beginning about this 3D kind of out of equilibrium quantum spin glass. You can say those things as well. This is kind of like the obvious application. Another obvious application is if you want to minimize classical Ising models for understanding classical materials or doing optimization. It would be really cool if you could just find ground states of this classical Hamiltonian. I would say in theory, an analog quantum computer should be a very good optimizer for these things. In practice, it's like a big mess because noise plays a non-trivial role. You kind of get thermal distributions from like weird states. But the team I work at Los Alamos has demonstrated, I think it's the first ever, like real runtime advantage for quantum-based optimization. And I would recommend checking out that paper if you're interested. We show that, like a 50x runtime gain for the hardest problems that we can find. Wall clock, real wall clock time experienced by the user. So that's actually a pretty encouraging sign. If the system just gets, 2x bigger, it would probably be like a dramatic performance benefit that would be more like a quantum advantage demo. So that's also like an obvious application. Here are some less expected use cases of quantum annealing that have come out since we've had these computers to play with. So the first one is that I mentioned before, you might want to do classical sampling or sampling from the classical Ising Hamiltonian. In theory, you shouldn't be able to do this with a quantum annealer because of some peculiar behaviors of the quantum annealing algorithm. The X driver will not give you like a Gibbs distribution from the classical Hamiltonian. But what we showed in these papers was that it does seem that some weird interplay with noise in the system and thermal effects can give you something like a Gibbs distribution of the classical model. So we designed like a special way of operating the machine so that it produces these statistics. We don't have a good theoretical explanation for how that happens because it's an open quantum system, but it has great potential for applications in machine learning and classical physics simulation. So that's one unexpected one. I would say the other really unexpected one is Gibbs sampling from the transverse field Ising model. So this is now looking for states of spin configurations in a thermalized distribution, but where the transverse field is actually playing a non-trivial role in reproducing those. And this has really been driven by D-Wave. So they've produced a bunch of different papers reproducing different phases of matter in kind of well-understood systems. And the thing about this is that you're doing Gibbs sampling from a quantum distribution that's, quantum Monte Carlo or path integral Monte Carlo, the standard diagrams. And there's some very nice work by D-Wave as well, showing that if you use a reverse annealing protocol in their system, you can actually produce these statistics like 10 to the 6 times faster than best known classical alternatives. So that's also a really encouraging, surprising thing. So those are 4 things you can do with this hardware, 4 types of computations a weird analog quantum annealer might, do for you. So what are you going to do with these weird things? What would be a high impact application of a quantum annealing? And that's what I'm going to spend the rest of my talk trying to convince you of. Let's begin with magnetism. So at the, broad section of magnetism as a scientific field of study, where most of us are used to using ferromagnets. So that's like, using a magnet to pick up something, like with the a magnet, or on a hard drive, right? The old school hard drives have spinning disks, and like you use a magnetic field to program up or down on a bit of information on that hard drive, right? That's all ferromagnetism. The interesting scientific questions around magnetism these days, like what we study at Los Alamos, are all on frustrated magnetic systems. So on the right-hand side, you can see like if you have three spins and they're ferromagnetically coupled, they all want to align together. But if you have spins where some are ferromagnetically coupled and some are repulsive, so anti-ferromagnetically coupled, you can actually have degenerate ground states, or states where equivalent states where the spins take different values of up and down. So a lot of the research that's happening in magnetism these days is looking for exotic states of frustrated systems. So some way that a material has frustration in it so that you get quasi-particle effects, or you have a liquid type of phase where the spins are kind of always moving in time. And those have potential applications for like next generation storage, lower energy consumption, lower energy consumption for electromagnets, potentially superconductors. So there's a variety of things that people want to understand these weird frustrated magnetic systems. To that end, NSF pays for a facility called the Magnet Lab. It's a pretty big effort, about $40 million a year of scientists. There's a hub in Florida for this Magnet Lab. And then there's also a facility at Los Alamos, which is where, I learned about the Magnet Lab. And essentially what they can do in these experimental facilities is they can cool down crystalline materials to, a few Kelvin, and then they can hit them with ginormous amounts of magnetic field. So like Lanel has the world record, or at least it was a world record at some point, of like hitting a material with 100 Tesla for like a microsecond. And also Lanel holds some records for like the longest sustained, 60 Tesla pulse into a material. And so these materials, they're not very magnetic. Like in the way we interact with them, they wouldn't seem magnetic. But when you hit them with this much energy, you actually see really exotic things happening. Some of the interesting impacts they've had at the Mag Lab, they were one of the facilities that first showed that you could see the quantum Hall effect in graphene at room temperature. They've, studied all sorts of interesting properties of graphene and superconductivity. But in general, they get about 20 to 30 new materials per year. And the reason why those materials are going to the Mag Lab from everywhere in the country is because, classical simulation methods, lower energy analysis methods have not allowed scientists to understand these materials. Here's a picture of basically what they do in the Mag Lab. There's experimentalists, they prepare the samples in these kind of dilution refrigerators. They put them into a cryostat, lots of liquid helium involved, and they cool down the materials. You have a really big generator, which was salvaged from 3 Mile Island, which is used for building these crazy magnetic fields. And then they do all sorts of different experimental protocols. Like one example here is doing a phase diagram where they sweep magnetic field and the temperature of the material, and they try to understand its different phases. And so that's kind of the experimental protocol. I'm a computer scientist, so like more towards a math or theory abstraction. So the way I think about what they do is that we've got a sample, we can apply like a transverse field and a longitudinal field. We can measure net magnetization of the sensor. And then they run essentially a time-varying protocol, which is on the right. So you start with the material at some highish temperature, you cool it down over time without usually applying any field to the material. So that's the blue line. And then they'll do, like one example is an up-down sweep protocol. So they'll take the longitudinal field and they will just like ramp it up to a specific Tesla and then ramp it down. And all of this time that they measure what the net magnetization is, and they see what happens. So that's one example of a protocol they would run. And then the key idea is that by combining observations of different protocols, they get insights into the exotic properties of the material, but they never really know for sure because their observability is just the net magnetization of the material, like how up is it or how down is it. Interesting side note about quantum annealing. The idea for quantum annealing as a quantum algorithm actually came from one of these magnetic labs where they were using a very different protocol to try to get a material into a lower energy state by ramping a transverse field instead of while also cooling the material. So what is the value proposition of quantum computing in a laboratory like this? We want to use a computer to help people understand these exotic materials. And Vivian Zaff, who's like one of the colleagues, a senior person who works in the magnet lab, has explained to me that, when you do quantum Monte Carlo and you just look at thermalized statistics, you don't end up generating the right phase diagram and other observations. So like you can see in the top right here, that's a simulation of what this particular material's phases should be. And then the bottom is the actual data collected from the lab. So maybe qualitatively similar, but not quantitatively similar. So the hope is that a quantum computer could help you kind of bridge this gap between these two examples, like the simulation we have above and the real data that's below. And so hopefully, if this all works, quantum computers will let us do new things here that we can't currently do in the lab. So we can simulate the materials, we could understand their behavior, the spin configurations on the micro scale, and it would help us search for the right Hamiltonian to represent the material. And then, of course, we could do pre-screening of material candidates. If we're looking for a specific type of property, we could test them with the quantum simulator first before having to go and test them in the laboratory. So lots of potentially useful things. So that's the mag lab. What does it have to do with quantum annealing and all the stuff I told you before? Let's dig into a really specific example. So here's calcium cobalt oxide. So this is a particular spin system that came to the mag lab some years ago, and they've been studying it because it has unexpected properties. I'll show you exactly what that is. There's this very nice paper from PRB about trying to reach the equilibrium state of this magnet. I think this magnet is particularly interesting because it has ferromagnetic interactions and antiferromagnetic interactions. So there's kind of like some frustration in that. But you see other interesting properties. Like that's a picture of kind of the crystalline structure of the magnet, but I'll go into it in a bit more detail. So in this particular paper, PRL paper, they studied the system. Essentially, it's like a long chain. So you can think of it as like a plane of triangles that are all lined together. Like if you look at the red dot over there, and then there's these layers of triangles are stacked on each other, and they interact with the 3 layers up, 2 layers up, and 1 layer up with ferromagnetic and antiferromagnetic interactions. The dashed line is antiferromagnetic and the solid line is ferromagnetic. Or I might have gotten that reversed. Whatever's written on the slide is right. And in this paper, they studied 50 layers of this material on 12 by 12 lattices. But I think the important thing to see is that this material is an Ising-like material. So it has a Hamiltonian, which everyone believes is like a transverse field Ising model. So here you can see the hypothesized Hamiltonian of the material. It's very similar to the transverse field Ising model, which we studied, or which quantum annealing can look at. And then there's the particular values of J, which are proposed for this material. So I think the thing that makes this unique is that normally in the mag lab, they avoid Ising materials because they don't have a good simulation platform. But now we have a potential simulation platform. So maybe we should have a second look at these Ising materials. here, for this specific material, here is an example of the data they get in the lab when they do this up-down sweep protocol that I mentioned before. I think focus your attention on the blue dots on the left figure. Essentially, what's happening here is they're doing the up sweep on the blue dots, and the magnetization kind of increases as they increase the external field. And then once they get to the top, they do the down sweep, and there's kind of some residual energy in the material, and it comes down. So the thing that is really interesting and surprising about this material, okay, I'm going to get to it in the next slide. So if you look at just the ground states of this material, what you see is, they call it the 1/3 plateau. If you studied the Hamiltonian I showed you before in detail, you'd realize there's like an obvious ground state, which is just like 1/3 of the spins go up and 2/3 go down. So if you actually had like a perfect, if you had the ability to repair the ground state every time, you would just get this flat line, like 1/3 magnetization. And at some point, your external field becomes so strong, you get 100% alignment. You overwhelm the material's properties. But the thing that's fascinating about this material in lab is that you don't get this 1/3 plateau. You actually see 3 unexpected metastable regimes. So these are points in the material where you would expect it to be in the ground state as 1/3 spin configuration, but actually you don't quite reach that property. And these are the not well understood phases of the material that we're trying to understand with a better simulation. Qualitatively, quantum Monte Carlo can reproduce this, but not quantitatively, which is the hint for why you probably need a quantum computer for this. Now, here is the really fascinating thing. In this paper, quantum annealing simulation of out-of-equilibrium magnetization in a spin chain compound, they look at exactly the same material. They realize that there's a pretty close, pretty natural way to embed it in the hardware native graph of this D-Wave computer. And they use the transverse field Ising model to study it. They essentially run what's a reverse annealing protocol, which is very similar to like an up-down sweep, so that they can emulate the up phase of this experiment. Yeah, so essentially, like if you just want ground states in a quantum annealer, you just anneal forward. But D-Wave's platform allows you to start in a specific state, go backward. So now you're in a weird mixture of like a quantum and classical Hamiltonian. Let thermal and quantum fluctuations change your state, and then go forward again to measure what you see. And they've shown that, like, if you repeat that a bunch, you can actually get statistics from all sorts of weird out of equilibrium distributions. So this is the shocking and magical thing. We have the quantum Monte Carlo simulation on the left. We have a emulation of the same protocol on the D-Wave device in the middle. And on the right-hand side, you have the actual experimental data that was collected in the lab. What I'm going to show you in the next picture is if you take the relevant data from each one of these plots and you put them together, you see something quite surprising. So here's the picture. So on the right-hand side, you've got, this is the upsweep protocol that they run in the magnet lab. The black dots are the real data from the real material in the lab. The green dots are from the quantum Monte Carlo simulation, and then the pink dots are from the quantum annealing study of the system. So once you adjust, like you normalize the energy scales, it immediately appears that the quantum annealing approach is like a better qualitative match to the real model in the lab. And on top of that, it's really much faster. So like collecting the data in the lab would take a couple of hours. To run the simulation on the quantum annealer, we're talking about a couple of minutes. To do the quantum Monte Carlo simulations, you need quite a bit of classical compute. So it's like on the order of days to weeks on a small cluster. So it looks like this quantum annealing approach can actually access this kind of dynamics trajectory of the metastable plateaus. which is out of scope of quantum annealing or quantum Monte Carlo, but that's still a bit of an open point that is to be investigated, but this is a very encouraging sign. And it's much faster. Now, I'll try to show you in the next slide what you can do that's really unique and interesting is that because in a quantum computer or in a quantum annealer, you can observe the state of every qubit once you go through the reading procedure, it allows you to inspect the material or the system in a lot finer detail than you can do in a laboratory setting. So if you zoom in on like this particular metastable, like there's 3 metastable plateaus, and you look at the results that are coming out of D-Wave's computer, it's quite fascinating. So maybe let's focus on the picture on the right. If you find a true ground state of the material in this regime, it has a long range order, right? This 1/3 up, 1/3 down. That's the picture on the right. So like you can see that there's a common pattern to how the spins are pointing, are black or white, which means up or down. Now, once you, if you don't get the ground state and you look at one of these out of equilibrium metastable states, you see something more like the green and blue and red picture. So there are actually kind of islands of order that are forming, that are consistent, and then they're like not, it's not the same across the whole system. There's like different areas that are blue and green and different areas that are red. So that's showing kind of like that there was an island that formed that's ordered, but it's not, it's inconsistent with the other islands that are formed. So this is kind of the beginning of maybe a hypothesis that there's maybe a glassy type of state happening here, like a semi-ordered state. But this is the first time people have even been able to hypothesize what's going on. This is the first time we've seen a spin configuration that matches this metastable plateau. So I would say this result seems too good to be true, because if it is, it really means we're ready to start, doing the Mag Labs science with a quantum computer in the loop and doing something useful with it. But I think these results are just kind of too good to ignore. It would imply that a practical quantum advantage is already here if all of these results can be verified and replicated. So at Los Alamos, to that end, we're kicking off a new project that started a few months ago called Accelerating Scientific Discovery with Quantum Annealing. And essentially, we're going to test this hypothesis, like, can we really discover a new material in the Mag Lab or characterize a material's properties better than we ever did before with quantum annealing hardware as a key supporter of that scientific endeavor? And we have an interdisciplinary team. It includes career scientists. Alejandro is a theoretical physicist, and Ming Sung is our experimentalist. And essentially the way it works is that we're all kind of working in consort. My team helps support running experiments on different quantum computing platforms. The theory people are kind of proposing new models, while the experimentalists are trying to verify them in the laboratory, and we feed back across all these different sections. Our grand challenge is to find a new quantum spin liquid. That's a pretty ambitious goal, but you got to have something really great to shoot for. If we're going to even get halfway there, it would be valuable. Just to highlight how this works, I think the workflow is quite a bit different than the way we usually think about quantum computing. Normally, when we do a quantum computing study these days, we start with the quantum computer and we kind of say, well, what physics question could we ask about it? Here, we're going to start with the material samples. The most constraining property is what materials can they get and source into the Mag Lab. So we have a material sample. We build a Hamiltonian for that, a hypothesized Hamiltonian for that material. Then we try to understand that Hamiltonian in simulation using quantum computing hardware to assist in standard analyses. And then based on what we see in those experiments or in the simulations, we'll try to verify our understanding with very targeted experiments in the Mag Lab. And most likely, those will not match. We'll have to calibrate the Hamiltonian. We'll have to potentially revise some of its terms, and we'll iterate this process. And if we are successful at any point of really reproducing what happens in the mag lab, we should identify like a new exotic property of a material, like a quasi-particle or some other structural property that's very unique. So that's a very different workflow than usually we do. So I'll just wrap up and take questions. In summary, I believe analog quantum computing is not a transitional technology. It's not going to become obsolete. I think it's a really fast quantum computing technology, and that's really valuable right now. It's here to stay, I would say. And the primary challenge that we face with analog quantum computing is you need to find a section of physics problems that are open and interesting, that are a good match for the hardware's native Hamiltonian. That can be very difficult to do. That's kind of the Achilles heel of the approach. But we were able to do it, Lionel. It took us about 5 years. But I think we can do it faster now that we understand what to look for. And I would argue, for D-Wave's quantum computer, it's one of the most restrictive quantum computers that's ever been built. And if we can find this example for such a restrictive piece of hardware, there's probably a lot more applications with more general quantum systems, like ones where you could lay out your architecture in 3D. That's what the green picture is, or one where you can do very exotic continuous time protocols that aren't just the quantum annealing protocol. There's very nice work in labs showing that those exotic protocols can produce interesting results. So with that, I'll thank you very much for coming, and let's talk about any questions you have. Sure. Yeah. Okay, so the excellent question, I'll repeat it for anyone online. And I think your question was, do we have a reason to believe that quantum annealing is bringing something new rather than just being a faster quantum Monte Carlo? And I would say we don't know for sure, but I suspect that actually the combination of open quantum effects, right, here are actually valuable. So if you dig into the related paper, let me see if I can get back to this slide. Yeah. So if you dig into this paper that D-Wave produced, they show, like, in some ways of operating their hardware, you just get the ground state every time, right? They show in other regimes, you're basically sampling from quantum Monte Carlo thermalized state. And then this picture comes from an in-between that is not one of those two extremes. So that suggests that you're you have some open system effects, you have some dynamic evolution effects, some thermalization, but not dominated by any one. And I wouldn't be surprised if that's really what's happening in the material too. So I think the answer to your question is, I think there's something different going on here, but we just don't have the silver bullet to prove it yet. I think there's one up there.
So sticking with this picture again,
Sure.
if I were to look at those three plots, I would have said, that without knowing too much about it, I would say the green plot is showing something that is relatively idealized. It shows the steps in the right places, but they're sharp and clean. And the other two would indicate that something messy is going on in the system. Maybe there's some disorder, maybe there's some non-zero temperature, and those two things look like different versions of that messiness. Now, is that an inappropriate conclusion?
I think that's a reasonable conclusion.
So then I'm going to say, well, what it looks like is that your quantum annealing way of doing things is introducing some kind of dirt into the system, as is the data, but whether it's the same kind of dirt is not at all clear.
Correct. And that's why we need this project to investigate the details in a lot closer. I think let me ask you this question, or first let me say, like, you mentioned adding in some dirt. You know, and to answer the last question, my hypothesis is the dirt is like, you know, some kind of weird combination of open quantum system and like a unitary evolution in a regime that we don't have a good characterization for. So, and I think the way I would try to convince myself that's the case is if we can do a simulation and it's predictive of what we observe in the laboratory, then we're like, and it can be done replicate a few times in a few different systems, I start to get convinced it's the right dirt. If would it convince you?
Well, I guess I would have to see a better overlay between the black and pink pairs,
Yeah,
in order to convince me that you'd introduce the right kind of dirt, as opposed to just some random whatever. Now, and that's just looking at the pictures without knowing anything about what's behind an experimentalist.
I agree. And that's one of the first experiments we're doing on our project is we're reproducing this data so that we can then tweak different parts of it and really dig into the details. Thank you. Yeah. 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 No. Yeah. So the question, I'll repeat it for online, is like, you know, how do you arrive at this first initial guess on the Hamiltonian, and how do you know you're not so far off you'll be searching for a long time? So this is a bit out of my expertise because that's what the theorists and experimentalists do, but I can tell you what I've observed is that based on the crystalline structure, so somehow they kind of know the crystalline structure of the material. It might be through neutron scattering or some other kind of more fine-grained experiment. They have a pretty good guess at, like, you know, what the potential interactions of sites can be. So like you can easily rule out like that the interaction doesn't span like 2 or 3 hops from the nearest point. And so I think it's a combination of that plus just a lot of experience. The people who do these things have seen hundreds of materials in their life, that their initial guess seems to be quite good. But I wouldn't rule out that, say, like we might be off on the strength of an interaction by like an order of 2 or 3, right? And that is a parameter search we'll have to do. We have a very nice write-up about a different model system, which actually doesn't, it's a Kataev system, so it doesn't fit the quantum annealing model. But there's like 19 Hamiltonians that have been proposed, and none of them, there's no consensus on which one is the right one. And the quantum simulation challenge is like, can you use a quantum computer just to narrow down this list of 19 Hamiltonians closer to the set that are the correct ones? So it's a good question for sure.
And maybe the question is about benchmarking from like the students, and so because maybe I could think maybe because you're missing some kind of secret ingredient that you know for the dynamics to actually with that, or like what's happening in the system, even like classical simulation. Because like even when mechanism of like the I like kind of interpret that as like the condition is showing up as a technique very good is because of magnitude without knowing technical points. So like I guess the question is like have you thought also about like trying to look for what exactly like what is theoretically captures that kind of dirt and trying to simulate that possibly, and also kind of making connections maybe and like platforms that obviously make comparison in all regards is like sometimes if you know that like I guess in the dynamics maybe that it may or may not make the dynamics easier to simulate possibly. So I'm curious if you have comments.
Yeah. just to try to repeat the question and maybe condense it a little bit, validation and verification of, what models can reproduce this data, I think is kind of the heart of the question. I mean, I would say we're always interested in doing this. It always improves our understanding. The challenge we've been facing is if the hypothesis is that open quantum system effects are the primary important missing feature, right? The tools to simulate it at the right scales are just not adequate, right? So it's like, we can do open system dynamic simulation, like maybe up to 50 spins. I think that's on the upper end of what's possible. And you may not actually reproduce the right statistics. Like you might not have enough sites to avoid finite size effects. So now we're in this regime of like, well, we need some kind of a quantum algorithm, a quantum computer. So in the long run, what would be great is if we had a fault-tolerant quantum computer, we could just know it gave the right answer, guaranteed, and we could play with those hypotheses. In that regime, we could then verify that the analog quantum computer is doing the right thing. And then we could use the analog quantum computer at bigger scales and more general models. But I just don't see, people are always generating hypotheses, more general models, a missing term in the Hamiltonian, to try to match the results. But it's very difficult to do. With this material, our best guess is that it actually has to do with these open quantum systems and unitary evolution, but like, that's very much our best guess. Yeah.
So following up on that, so when you say quantum Monte Carlo, of course, there's a number of things that sometimes means. One of the things that it can mean, which I don't think is what it means here, is quantum Monte Carlo wave function on jump simulations, which are specifically open quantum systems. Right? That's a way of bringing a quantum Monte Carlo spirit, at least, in. Now, is that the kind of thing that is too hard to do with more than 50 sites, or is that something that people haven't tried yet?
So I'm not familiar with the quantum Monte Carlo methods you just said, but I can tell you a bit about what they did in this related paper. So in this paper, if you just run quantum Monte Carlo until it has converged, right, then it actually reproduces the 1/3 plateau. It starts to find like the right thermalized ground state. So what the theorist who was doing this did was he ran quantum Monte Carlo but truncated it. He like left it out of equilibrium, and that was the only way to like reproduce these steps. So he claimed that it was kind of like a halfway between like an evolution and a thermalization. But like, for me, there's no mathematical basis for that. So like, I wouldn't go that far.
So maybe after
Yeah.
we can
Sure.
talk about this other kind of quantum Monte Carlo that might be useful.
Right.
Okay, so let me, now I've got to make fun.
Oh gosh.
So in the protocol that you described, where you pull something down to somewhere between 2 and 10 and then do stuff like pulse on a great magnetic field.
Yeah.
What I'm wondering is, what is the characteristic temperature with respect to which 2 or 10 or something is low or not low? That is it the Néel temperature? Is it the Curie temperature? Is it the Fermi temperature? Do those things even make sense for the kind of system you're looking at?
So I don't know most of what you said. So I'm not sure. However, I can tell you that what I do know from talking to our experimentalists is that different materials kind of have different native energy scales. So some at like 2 Kelvin will behave very much like a closed system because the energy scales of the material is just so strong compared to the environment. Others will behave more like an open system, even at 2 Kelvin, because it's not cold enough. And that's one of the reasons why they sweep temperature, because they're actually looking for like, when do the certain types of effects get diminished or amplified. And so we pick the materials that we think have the right type of noise impacts at the right temperature. I think we're at time, so maybe we should just wrap up. Thank you all for great questions.